previously we looked at projectile motion, a vector approach. There is another approach we could take. These were the motion equations basically that we came up with. Now if you look at it, essentially they're just parametric equations. T is the parameter. And because of the equation, we see y equals this and there's the t squared, x has got something t. Yes, of course, it turns out to be a quadratic or a parabola, which we know projectile motion is. So we could use what we know about quadratics and the parabola to solve these problems. Now, let's work out the actual equation then of the path of the particle. I'll make x the subject of t and then substitute that into the y. That's going to be easier than trying to do it the other way around. So sub that into y, there it is. I mean, that's a quadratic equation, but we can make that look nicer because sine on cos is of course tan and the reciprocal of cos squared is sec squared. And then for the sake of solving equations, changing that sec squared into 1 plus tan squared, and then that would make it a much nicer equation. So back to our common questions then, how would we approach them now? One of them, remember, was what's the range of the particle? Well, now we're basically saying, well, what's the roots of the quadratic? Because that would be the x-intercepts, or when it hits the ground. And so we would solve this equation, and I end up getting two possibilities. X equals 0, or x equals 2v squared sine theta cos theta. Well, 2 sine theta cos theta I can change to sine 2 theta. And if we're talking about the range, well, clearly it's not the x equals 0, that's where we started. So the other one must be the range of the particle. What's the greatest height? Well, now we're talking about where's the vertex of the parabola, but I'm only interested in the y value. And remember, we can find that with minus the discriminant on 4a. So sub that in, and eventually it comes down to this. So we get v squared sine squared theta on 2g. So that would get us the greatest height. What angle does the particle make with the ground, or any other particular point? But with the ground, we essentially want to find the slope of the tangent at whatever point we're investigating. And then once we know that, we know slope equals tan theta, and we can find the angle. So let's go back to the same example that we did before with vectors. So our ball's thrown, velocity 25 meters per second, angle inverse tan of 3/4. We're going to determine, well, first of all, we're going to need to work out what the Cartesian equation is for that particular parabola. So we did work out that x was 20t, so t will be x on 20. We also worked out an equation for y. Subbing that in, there's our quadratic. The greatest height was one of the questions we had to ask. Well, what I'm saying is y value of the vertex. So now I can go, well, that's minus the discriminant on 4a, and there's the answer we saw before, for 45 on 4, but it makes more sense to say 11 1/4 when we're talking about, oh, how high is something. The range, okay, let's solve that quadratic, and we get 0 and 60, so the range is 60 meters. Velocity and direction after half a second. Okay, so differentiate it, because I want to know the slope of the tangent. So there's my derivative. It was when t equals a half, so I'm going to have to work out what x is, but that was an easy equation. X was 20t, so we know x is 10. Up that in, we have a slope of a half. So there's the angle, 26 degrees 34. The velocity, well, x on t cos theta. Drew up my triangle. I suppose I could have used the 2634, but by having the triangle I can get the exact value. And subbing that in, 10√5. And that was the answer we saw before there. So knowledge of the quadratic, rather than using the calculus, may be a quicker way of solving some of these problems. So add these ones, and they're more ones where we can take the parametric approach rather than the vector approach.